Comments, questions, concerns on page 1. Is there anything anyone would like me to go over? Kaylee's not here to catch my mistakes. So someone else better. No one caught my mistakes in the first block. I don't think anyone in the previous block did their homework, so. Shots fired, block C. If any block C's read or watch this video. Okay, going once, twice, thrice. Sold. Flip the page. Here's questions 2 through 4. Take a look, see if you need me to go over anything. Comments, questions, concerns on any of this. Going once. Going twice. Going thrice. Yes. The first question? Well, where are the first questions on the last page? Or do you mean question number 2? Question number 2. A spring with a K value has been extended. It's just E equals half KX squared. You know the compression, you know the spring constant. Just plug it into this formula. You should get 3.8. Brooke. Same question, but like 2C. I guess the C is only has 2. Okay, so that is the X value. That's the compression. And that's the energy. So you just plug it into E equals half KX squared. That's 26 equals 1/2 K times 0.2 squared, and you solve. Isolate for K. Me neither. Well, you should have gone 0.2 squared is 0.04 times 0.5 is 0.02, and then 26 divided by 0.02 is 1300. Yeah. Okay, anybody else? I can flip the page. Going once, twice, thrice. Sold! To me. 5 through 8, here they are. Are there any comments, questions, concerns on any of this business? Anything anyone would like me to do? That's your final answer there. Okay, going once, twice, thrice, sold. Well, because because you did the homework, right? So you're just checking your final numbers, right? Uh-huh. If you didn't do your homework, I'm not going to give you time now to do it. This is not the time to learn it. Yeah, it's the circled parts. That's the answers. 0.6, 3.26, 0.031, 43.8. You're not supposed to write down all of the methodology. You're supposed to you should have the methodology. You should have an answer, and you're just comparing what you got to this thing. You got to tell me you're better than Mr. DeVries' calculus students. How bad are they? Mr. DeVries was very upset this morning when I went in there. He gave them 10 questions, 20 minutes at the end of class on Friday, and all weekend to do 10 questions of calculus final exam review. So these are grade 12s who are taking calculus because they need it for university. These grades are going on their transcripts. How many students do you think did any of the questions? One student did one question. And they wonder why they're failing. In calculus, just to give you more perspective on a calculus course, in a calculus course, nobody should be in there getting less than a B. Because by that point, I mean, if you're taking calculus in high school, it's because you need it. And no one takes calculus for fun. Mr. DeVries, before this semester, had never given below a B in a calculus class. And this semester, he has students failing. How dare you? You need to actually do the work, so be better than them. And here's question 13. Is there a question 14? No, this is the last one. Comments, questions, concerns? It'll all be in the video. I'm currently recording my going through this, so you don't need to. You can take pictures, but you are not obligated to. You can always go back, watch the YouTube video, and pause it if you need to see how questions were done. If you didn't do your homework and then are going to go back and do it before we do the unit test. You were here on Friday. You should have. You were not? Oh, yes. No, you were not. Across the table from you was. Nielsen was also not. But did I post my videos from Friday? I feel like I may have. Let's check. If I didn't post the videos, it's my fault. If I post the videos, it's your fault. Dun, dun, dun. My fault. Videos are still. You didn't even check. But no, I did not post the videos from Friday, and I totally forgot. Busy getting tanned. That's right. I don't know. Yeah, so yeah. Getting your tan on. Get your camp on. Okay, so here we go. This will probably be our second last lesson in this unit. Nuclear decay. Here we go. Now the marks are in my head. I will hand them back tomorrow. I know, but then I forgot to hand them back to my C block, so we'll hand it back tomorrow. Because I like to keep you guys on the same path. Yeah. So I forgot to give theirs back, so I'm not giving yours back. I'm intentionally withholding. But again, the grades are on my head. You can see where you're at. It was out of 47. There's still 3 people who need to write in this block. 4 if you include Mahip, but we're not going to do that. Here we go. Nuclear decay. It might feel weird to throw this into this unit on energy. We've looked at kinetic energy, gravitational potential energy, and we've looked at spring potential energy. Nuclear decay is a massive source of energy, which we will explain how that happens tomorrow. But to be able to explain how it's a source of energy, we need to explain what it is first. And so today's lesson is all about nuclear decay, and I told you balancing would come back. Here it is. So, recall, atoms have 3 subatomic particles, protons, neutrons, and electrons. What can you tell me about protons, neutrons, and electrons? Anything. What do you remember? Protons are positive. Electrons are negative. Neutrons are neutrally charged, so they have no charge. That's very good. What else can you tell me about these things? Nielsen. The protons and the neutrons are found together where? In the nucleus. Thank you. What else can you tell me? Anything. Any fact that you can tell me about protons, neutrons, and electrons? Brooke, you got something else? That hand? These guys are found in the outer shell. You betcha. Brooke, you were about to say something before I called on Nielsen? I thought you were umming while she had her hand up. Okay. Was someone else umming? Evelyn, you got something to say? Not related to where we're going this year. So she was like, that's static. We're not talking about static. It's a lot more energy in what we're about to talk about than that. What else can you tell me about protons, neutrons, and electrons? Positive, neutral, negative. These two are found in the nucleus. This one's found in the outer shells. There's one more thing that you could tell me. What is the mass of an atom made of? Which of these three particles contributes to the mass of the atom? It is not all of them. Protons and neutrons. So it's the nucleus where all the mass is found. So protons plus neutrons give us the mass of the atom, which is an important fact that we're going to play with today. Electrons are so small that they do not contribute to the mass of the atom. They are not massless, but for all intents and purposes, we ignore their mass. But it is important to recognize that they do actually have it. It's just so small that we don't care about it. So, when atoms gain or lose electrons, like remember, the electrons are in the outer shell. You can be positively charged by losing one of those. You can be negatively charged by gaining another one. But as soon as that happens, we have a name for that thing. We call it an ion. Atoms can gain or lose other things, though. It's not just electrons that can be lost. We haven't talked about this yet, so this is not a recall. This is brand new. When atoms gain or lose, what's the other thing an atom could gain or lose? What defines what atom you have? The atomic number. The atomic number is not allowed to change. If you have carbon, carbon is atomic number 6. It means every carbon everywhere in the universe has 6 what? Protons. So when you change, the protons are not allowed to change. When you change the electrons, you get an ion. What's the only other thing you could change? How do you change the mass if you're not allowed to change the protons? No. You're right. Keep going, Evelyn. If you're changing the mass but the protons are not changing, what are you changing? The neutrons. Neutrons are allowed to change. You are allowed to gain or lose neutrons without changing anything other than the mass. When atoms gain or lose neutrons, ions are what we call when we gain or lose electrons. When we gain or lose neutrons, we call these isotopes. And here's an example of isotope, what I mean by when I say isotopes. So hydrogen. Hydrogen, symbol H, both of these are going to be hydrogens. Every hydrogen has the same atomic number. The atomic number is 1. We're going to put that down there at the bottom. This is the atomic number. Every hydrogen has the exact same atomic number. If you look at your periodic table, I want all of you to flip, the person sitting beside you, make them flip to the inside front cover of this booklet. What is the atomic mass listed there for hydrogen? Make the person next to you flip the page. Atomic mass of hydrogen on that table is 1. What does that mean? It means that a single atom of hydrogen has how many protons and how many neutrons? If the mass is 1 and there's 1 proton, the atomic number is 1, how many neutrons are there? 0. A normal standard atom of hydrogen has 0 neutrons. But out there in the world, you can find hydrogen atoms, so single protons, that have neutrons attached to them. One form of this is actually hydrogen 3. So these numbers up here represent the atomic mass. What's going to be special about hydrogen 3? Still only has one proton. How many neutrons does it have now, though? Sorry, Evelyn? It has a mass of 3. So 2. And the way we name these things is we give them the name of the atom. So this would just be hydrogen. This one would also be hydrogen. But to differentiate between the different isotopes, we give their mass added on as part of the name. So this would be hydrogen 1. This would be hydrogen 3. There are certain special isotopes that we give certain special names to. So in addition to calling this thing hydrogen 3, which it is, we also call this thing tritium. It's the example that I have down there. It's common enough in the world that we give it another name. Let's call it tritium. And it has some uses. It has an interesting little life, which I'll tell you about in a second here. Okay, so there's a bunch of examples of these different kinds of things. Cobalt. I want you to have someone next to you, your person sitting next to you, flip and find cobalt on the periodic table. What does it say the mass of cobalt should be? So what do we do with the mass when we find it on the table? We round it up. So 58.9 is going to become 59. So cobalt, as it exists most commonly, you will find it in the environment with a atomic mass of 59. But sometimes you will find cobalt as cobalt 60, one more neutron than cobalt 59, and that singular extra bonus neutron actually makes that cobalt radioactive, and we use it as part of the radiation therapy to prevent cancer. Not to prevent cancer. Prevent is the wrong word. Treat is the correct word. Cobalt 60 is one of the radioactive isotopes that we use to treat cancer. My mom had breast cancer a couple years ago. She didn't have to have chemotherapy, but she had radiation therapy. The radiation therapy that she was given used cobalt 60. Kills your cells, which is why they try and target it on the cancer.
Which one is worse in terms of the side effects? Radiation or chemotherapy? Or both combined? Hard to remember.
I mean, they're both nasty. One's a chemical poison, one's a...
Agreed.
I mean, my mom, because of where her cancer was and where the radiation was, she has permanent heart damage. That's just a byproduct of, it's better to live with a slightly damaged heart than have the breast cancer kill you. It's harm reduction. But as a result, my mom will never have the stamina that she had before. She gets tired quicker, and will always get tired quicker. But she's going to live to see her grandchildren grow up, which I'd rather get a little bit tired quicker than, be dead. And then, I don't know, chemo's its own beast. Adam. I can't speak to either one. I just know that cobalt 60 is part of the process. Iodine 131. What's the mass of iodine supposed to be? Make the person next to you flip to the inside front cover. Iodine should have what mass? 127. So how many more neutrons does iodine 131 have? 4 more. You take iodine, you strap on 4 more neutrons. The protons haven't changed. You just now have a more massive form of iodine, iodine 131. And iodine-131 is used, it's also radioactive. It's used to locate tumors. So cells in your body absorb iodine at different rates. Cancerous cells absorb iodine quicker than non-cancerous cells. And so if you're trying to find cancer in the body, you inject the body with iodine-131, and the cancerous cells will suck up that iodine quicker than any of the other cells. So you'll get parts of the body that concentrate with iodine-131. Because we're going to see here, because it's radioactive, that particular isotope of iodine is radioactive, you can now use radioactive imagers to find where the iodine has gathered in the body. You can now start to identify where tumors are located in the body. It's a really quite of a cool little thing. And tritium has some fun uses. It's a byproduct of nuclear reactors. It's found in the upper portions of our atmosphere when cosmic rays from space blast our atmosphere. And one of its uses, hands up if anyone in this class is currently wearing an analog watch. Anyone have a watch with hands? No, I'm not wearing mine today. The glow-in-the-dark portion of those regular watch hands is actually made from tritium. It absorbs light, glows in the dark. Fun little bonus fact about tritium. It's used in safety signs to help them glow in the dark. Yeah, it's also got some fun little applications. Also radioactive. So what does it mean for things to be radioactive? If isotopes have too many neutrons compared to the protons that they have too much energy. They become unstable. And things do not like to be unstable. Unstable things will do what they need to do to become stable. If you're sitting on an unstable chair, what will the chair do to stabilize itself? Fall over. It will change its orientation until it stabilizes. And if it means throwing you off in the process, so be it. Unstable things do not like to be unstable. So with elements, when an element is unstable, it wants to release whatever is causing its instability. And so because of that, there are 3 different ways that this can happen. 3 different kinds of radioactive decay. And all radioactive decay is a result of this instability. The extra energy and mass, incidentally, that is released from isotopes is transferred through radiation. And radiation is a way that energy is transferred in the form of electromagnetic waves and particles. There are two kinds of particles that we're going to look at that help carry away this extra energy. So, nuclear decay. Nuclear decay is the change to an atom due to the emission of particles or energy. It's a way of high energy isotopes to release their energy. And we've harnessed, as I've given you examples a little bit higher up, we've harnessed this in a bunch of different ways, useful ways. So the 3 types of nuclear decay that we're going to look at are called alpha, beta, and gamma decay. In order of, alpha, beta, and gamma are the first 3 letters in the Greek alphabet. It's like saying A decay, B decay, and C decay. But A, B, and C makes you sound lame, so we take the Greek alphabet, makes you sound educated. Alpha, beta, gamma. It's also better than calling them decays 1, 2, and 3. So when you're ready, flip the page. Alpha decay. Alpha decay was discovered in 1899 by a dude whose name you should know. No. You know, you were warmer with Einstein. No, the dude in the chair was alive, was not born yet in 1899. The dude in the chair is Stephen Hawking. Thank you very much. He died recently. Yeah. But, like, I mean, he was on The Simpsons. He wasn't alive in 1899. Okay? So 1899. There is a group of scientists from the late 1800s, early 1900s that you would have learned about in grade 8 and grade 9 as you looked at the different models for the structure of an atom. Bohr is one of them. This guy is actually the guy who taught Niels Bohr. Go back a step. Who was the guy before Bohr? I actually had to do a paper on this guy in Science 8. Long essay on this dude. Nope. Lewis was after Bohr. Lewis diagrams came after Bohr diagrams. Let's go back a step. What do you remember about the discovery of, who discovered the nucleus of an atom? He discovered them using gold foil experiment. Shame on all y'all. His initials are ER. Boo, Brooke. Yes, Ernest? Goes to camp? No, wrong Ernest. Ernest? Come on. So Ernest Rutherford did his gold foil experiment. Ernest Rutherford is the guy responsible for discovering that elements have atoms. He took a really thin sheet of gold foil and he shot alpha particles, these guys. He shot these guys at the gold foil and saw that some went through but some bounced. He had his big detector. Shame on your Science 9 teacher for not going through this. Let's blame them, not you. Except for Coppendale. Who else? Coppendale and Kaylee and Accordy. Who else had me for Science 9? No, Accordy's here. Coppendale had me. Kaylee had me. Asia had me. Kohi, were you in my Science 9 class? You should have remembered. Shame on you. I'm not taking the blame for that one. Yeah, Ernest Rutherford, 1899, did his gold foil experiment. He used the fact that a hunk of this material created, spontaneously it seemed, these particles that then just kind of, he guided them and they launched out and bounced off nuclei. What he later discovered was that these alpha particles were a singular particle that contained 2 neutrons and 2 protons. If you look at this, anything that has 2 protons is what atom or what element? What element has 2 protons? What is atomic number 2? Helium. If you have 2 protons, you have to be, that is the definition for a form of helium. So what he found was this hunk of rock that as it sat there, spontaneously launched chunks of helium. The helium, yes, exactly. What? This is confusing. This should be. The discovery of radioactivity was a confusing, mind-blowing process such that Nobel Prizes were awarded for this. Marie Curie is the only woman, she might be the only person, she was the first person and might be the only woman to win 2 Nobel Prizes in different fields because of her work with radioactivity. She got a physics Nobel Prize and a chemistry Nobel Prize for her work with radioactivity. She worked with radioactivity. No, but her casket is currently lined with lead. Her body was so radioactive after her death. Yeah, she was buried in a lead box. You can go see her body. Or like go to her tomb. It's lined with lead because she was so radioactive because of all of the work that she did. Her apartment is actually part of a museum exhibit, and it's radioactive because of the work that she did. Or she paid for her research literally with her life. So, alpha particles are the release of a singular particle that has 2 neutrons, 2 protons. 2 protons defines it to be helium. There's a lot of discussion going on underneath everything I'm saying. And 2 neutrons, 2 protons gives this thing a mass of 4. So there's the atomic number, there's the atomic mass. Atomic number 2, atomic mass of 4. But it's just the nucleus part. It's not the outer shell part. So alpha particles have the same number of neutrons and protons as helium. And so sometimes it's written as He and sometimes it's written as alpha. You'll see either one. When an isotope, when a hunk of this material undergoes alpha decay, the isotope spontaneously releases 2 neutrons and 2 protons in a little clump. And what this means is for the isotope to do this, that means if it loses 2 protons, what has to happen? If 2 protons leave, what has decreased? If protons leave, what has changed? What do protons dictate about an atom? Protons tell you the atomic number. So if 2 protons go away, what happens to the atomic number? The atomic number does what? Protons have left. So the atomic number must specifically, how does it change? How? You have an atomic number of 8, which means you have 8 protons. 2 protons leave. How many protons do you have now? 6. So the atomic number is now 6. The atomic number goes down. And if the atomic number drops, it means a new element is now present. Yes, that look of confusion is exactly the look that you should have. It just does. It just is. It just does. It just does. Why? Well, because the universe says so. I don't like that. The universe doesn't really care what you think. This is what happens. So if you lose 2 protons, the atomic number goes down too. But you also lose 2 neutrons, which means the atomic mass goes down how far? The mass goes down. Well, it goes down 2 for the protons and 2 more for the neutrons. 2 plus 2 is 4. So all that mass leaves when the alpha particle leaves. This is weird. But we know that this happens. It happens spontaneously, all on its own. An example of this is radium. Radium with a mass of 226 is unstable. Yeah, I know, right? You hear radium 226, you're like, oh man, that is an unstable piece of radium. So radium, in an effort to stabilize, emits an alpha particle. So it started with a mass of 226 and an atomic number of 88. When it emits the alpha particle to try and stabilize, it takes 4 of the mass and 2 of the atomic number with it. As a result, what you have is no longer radium. It's now radon. Because when those 2 protons left, you drop from 88 protons down to 86 protons. And if you look at your periodic table, the definition of an element with 86 protons is Radon. So now you've got radon, and that radon happens to have a mass of 222. This is weird. It should make you slightly uncomfortable. And when the helium leaves, its presence leaving reduces the amount of energy that was here and stabilizes the compound. Maybe not enough. Maybe it's still unstable. And so then another decay might have to happen. So one example of this is U-233. U is the atomic symbol for what? Uranium. When we think of radioactive elements, uranium might be the first thing that comes to mind. So uranium-233 is unstable. It undergoes alpha decay. The alpha particle leaves, taking 2 protons and a total mass of 4 away. What's left is the 92 minus the 2 gives you, do what you gotta do, yeah. Watch the video because I'll post them today. Gives you an atomic number of 90. The definition for the atomic number of 90 is thorium, and you'll have a mass of 229 because 4 mass left. 233 minus 4 is 229. It just does. No, a bunch of different things do this. This should bother you, and that's okay. Okay, another example. This guy, Pu. Pu is plutonium. Plutonium might be another kind of element, might be another element that comes to mind when we think about radioactivity, because the atomic bombs that we dropped on Japan, and, well, not we, the Americans dropped on Japan in World War II, one of them was a uranium bomb, the other one was a plutonium bomb. Yep. They both suck. Wildly. They're both what? Fat Man was the uranium and Little Boy was the plutonium bomb. Because there was 2 of them and one was chunky and one was small. So Fat Man and Little Boy. Just due to the sizes of the weapons themselves. So plutonium also undergoes alpha decay. And these are easy to identify. Once you internalize what this means, alpha is always 2,4. So if plutonium undergoes alpha decay, 94 minus 2 is what? 90, which is how you know uranium is what's present. Because uranium has an atomic number, 92. 94 minus 2 is 92. That's how you know you have uranium. What's the mass of this uranium? Yes. Because plutonium started with a mass of 239 and 4 left when alpha decay happened. Always 4-2. And the interesting thing about this is this doesn't happen all at once. Because when we think about having a hunk of, if this was a hunk of plutonium, first of all, we don't be dead, but if this was a hunk of plutonium, we don't get radiation poisoning very quickly. This thing is made up of millions of millions of individual plutonium atoms. And every single one of those plutonium atoms, so like I've got atom, this is all plutonium. Each one of these atoms is made up of protons and neutrons. These individual plutonium atoms change at different times. So you might have your hunk of plutonium there, and as it's sitting there, this one might just emit an alpha particle, and now all of a sudden, it's now uranium. So you would have a plutonium sample that now has a little bit of uranium there. And this guy's going to, same thing, alpha particle. Now he's uranium. And so, how does he by alpha decay? That. Because it does. Because of the inherent instability of plutonium. Plutonium's like, I don't want to be this way. It's just, I don't know. I'm stressed. I need to de-stress. How do I de-stress? I get rid of something stressful from my life. I have a meeting I don't want to go to, so I cancel. I put down the phone, screw your meeting, not going. Oh, I feel better now. Same thing. Except it's not actually getting rid of responsibilities. It's like, you know what? I'm uncomfortable. I'm going to take off my shirt because it's too warm. Boom. Shirt's done. I have a different shirt underneath. I look different. But plutonium actually physically becomes something new. It's like, oh, I'm going to take off my shirt, and now I'm a dog. Like, I'm literally something new. Yes, you can watch this happen. I mean, it doesn't look like much because the rock just is a rock. You can theoretically go out into nature and pick up this rock. Boom, there's the rock. It contains some plutonium, but it's also going to contain some uranium. Some of the plutonium is also going to have changed into uranium. That's what a radioactive. You can measure the radioactivity of the object. You can measure these particles coming off the hunk of rock. Here's the extra confusing part. What about the rock? What's wrong with the rock? But all rocks are made of stuff. There's different elements that go into making up the rock you pick up off the ground. If you happen to pick up a hunk of rock that contains plutonium, it's going to be doing this. It's not good. This is not a good thing. But you might not know. And that's the other fun part. You'll pick up the thing, and it's not like you're going to pick it up and be like, oh, that's not. You're going to pick it up, and you're going to be like, oh, this is cool. And then you might take it home. Throw it in your backpack, take it home. And you don't realize that the thing you just picked up is radioactive. And now you're carrying around this radioactive mess. And it's going to slowly start to damage you.
What is that? Is that likely to happen?
No. It's not likely to happen. Uranium is mined in northern Saskatchewan, for example. So, but I mean, at this stage of global development, you are unlikely to stumble upon a uranium mine that hasn't already been discovered. So I would say it's very unlikely that this will happen to you. But interestingly enough, and I get this, yes, it's TV, but this can actually happen. What's more likely is that you will stumble upon a radioactive object that has been turned into something else. Like, computer parts aren't really radioactive. Things like medical waste. If the hospital decides, you know what, we have this machine that's treating cancer, so it had cobalt-60 in it, and they chuck it, if it's not disposed of properly, it might end up in a landfill. Now, all of a sudden, you have, maybe you're, I don't know, here's an example, a fictional example. Actually, only partially. My dad worked for the city of Abbotsford, and I was doing a science fair project in grade 8, and I needed to be able to go through junk metal to look for, I was looking for some specific piece I need to build something. So he took me to the city, works here. He said, okay, cool, here's all of our, we don't need any of this stuff. This is junk material. It's going to go to the dump, but it sits here first. We're going to store all the metal. Take what you want. It's all city work material. And so it's unlikely anything wildly dangerous would have been in there. But if you know the right people, all of a sudden you can get access to places where things are stored, and if something gets stored improperly, you can end up with something radioactive. Or worse yet, hello Emmanuel, you go to the thrift store. Someone has donated something that they don't realize. And MCC Value Village, they don't know. So they're just going to take the object, they're like, oh cool, this is a dish. And you can go to thrift stores today, and usually it's glass that has a slight orange tinge. But you can go to thrift stores today and buy uranium glass. And uranium glass was in the 60s and 70s, they made glass that had trace amounts of uranium in it. Because they glow and they're black like that. Was a big deal in the 60s. If you rolled in there with a Geiger counter, or a device that measures radioactivity, and you were like, because normally they just kind of crackle a little bit, crackle. You got to the dish, it would crackle a whole lot more. And now you know that what you have is uranium glass. And we don't use it. Now, they could. Depends on how much, and the damage, it all depends on how much you take in. There is a threshold where the damage isn't severe enough to kill you. But you cross that threshold, and now there's that. So the samples will change, and here's the extra kicker. Uranium does this too. So plutonium becomes uranium, and uranium's gonna do it again. It's gonna pop off another alpha particle and become something new. It's gonna become thorium. And then maybe thorium does it again, and it becomes something new. So you get this cascading effect where now all of a sudden you have what you thought was a sample of plutonium, but because of the radioactive decay, it's no longer pure plutonium. Parts of it are going to be uranium, parts of it are going to be thorium, and we'll explain that in a second. Some of it's going to be protactinium, some of it's going to be actinium, and it's going to the decay doesn't end until you reach something that says, oh, now I'm stable. Now I'm done. And with uranium, that stable final product is lead. So let's keep going. This is weird. That's just alpha. We haven't done the other kinds yet. So let's look at beta and gamma. When you're ready, flip the page. I'm ready, so you better flip the page. Here we go. That was alpha decay. Here's beta decay. Beta decay also discovered in 1899. Same guy. Ernest Rutherford. In his work with alpha decay, he also discovers beta decay. And so he discovers that there are some materials that emit these alpha particles and do one thing. There are different materials or different isotopes that decay using a different mechanism. This is the mechanism. So yeah, you guys thought the last one was weird. The last one just took existing protons and neutrons and expelled them. It's like me saying, y'all want to stop talking, you get out. I just expelled something that was already here. Beta decay is different. Beta decay says, you need to leave, but you don't get to leave. You're going to become something different. And a part of you is going to leave. Yes. Yeah. It's like, you know what, Evelyn? Evelyn, I'm done with you. Evelyn, no, Evelyn doesn't get to leave. Evelyn, you have to turn yourself into someone else. You are now Malik. You are him in your essence, your skin color, your attitude, your gender, everything. You are now Malik. And to become Malik, a portion of you had to go out the door. But not you, just some part of you. You don't get to leave. You have to stay. But you have to become someone different. Hey, Malik, you're now something different. So here's how beta decay works. Isotopes can also release their extra energy by emitting beta particles. A beta particle was discovered to be a fast-moving electron. Now, this is not the same as becoming an ion. Okay? There's electrons in the outer shell. They leave or join, and you become an ion. This is not that. This is, in beta decay, a neutron that is found in the nucleus of the atom, spontaneously on its own turns into a proton. It just becomes something new. Evelyn became Malik.
How does that work?
It just does. And in the process of becoming a proton, the neutron has to give up an electron. And not give it up. Sorry, give up was the wrong word. It spontaneously creates an electron out of nothing to become a proton. Yeah. Yeah. This is one of those things, you just need to accept it. We know this is true. We've witnessed this in the universe on a regular basis. Anything that undergoes beta decay. Nothing to do with teleportation. This has nothing to do with teleportation. This is the bringing into existence of something new. You became Malik, and in the process, spontaneously created out of nothing a hat that left the room. Yep. Just out of nowhere, boom. You're Malik, and now there's a hat, and the hat has to go. Yep, Evie is now Malik, and a hat spontaneously burst into existence and has to leave the room. Yep. 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 Yes. This is the correct response. Yeah. It's that weird. So, except it's not Evie turning into Malik, it's a neutron turning into a proton, and an electron springs into existence and gets expelled. So, for this to happen, though, mass and atomic number need to be conserved. Electrons have an atomic number of -1. And electrons have no mass. That's not entirely true, but they effectively have no mass, so we'll say they have no mass, even though that's not true. And so here's what happens. You have lithium. Lithium has an atomic number of 3 and an atomic mass of 8. When lithium-8 undergoes beta decay, an electron gets ejected and a proton forms. The reason a proton has to form and an electron has to form as well is because if you take 4 and -1 and you add those two numbers together, what do you get? What's 4 plus -1? 3, the atomic number you started with. The atomic number and the masses must balance. And because no mass was taken away, the atomic mass stays the same. Because, yes, because the neutron became a proton. So, here's 3 examples. Carbon-14. Carbon-14, Brooke, Evelyn, and Sarah, I don't know which of the 4 of you is involved in whatever discussion is happening here, but shh. Carbon-14 is inherently unstable. It undergoes beta decay. So, an electron gets emitted, so -1 leaves. If you were at 6 and you lost -1, what's your atomic number now? 6 minus -1 is? 6 minus -1 is positive. When you subtract the negative, it's the same as adding 1. 6 minus -1 is 7. 6 minus -1 equals 7. Sorry, Brooke? Because it left. Like it physically left. Boom, shoots out into space. The hat is gone. Brooke doesn't get that reference because Brooke wasn't here when we talked about you turning into Malik and spontaneously creating a hat. But yes, boom, hat's gone. In order for the hat to leave,
Where does it go?
wherever it wants, it shoots off in a straight line until it hits something else. So what's going on here? That's tritium. Hydrogen with 2 extra neutrons undergoes beta decay. Beta is always 0, -1. So what is this atomic number? What does this number, yeah, who said that? Louder. 2. These 2 numbers on the right-hand side need to add together to give you whatever's on the left. 2 minus 1 is 1, or 1 minus -1 is 2. No, 6 minus -1. Don't make it harder than it needs to be, Evelyn. As soon as you bring in algebra, it's probably harder than it needs to be. You're okay. Another one. Technetium, Tc. Mass of 99, atomic number 43. When it undergoes beta decay, and an electron springs into existence and shoots off into the world. Boom. What does technetium turn into? 43 is going to become? Nope. 44. The number of because for this to happen, the neutron turns into a proton. The atomic number goes up. And technetium becomes Rutherfordium. The mass does not change. This is a 0. So this mass needs to remain the same. So now let me explain what's on the board over on that left-hand side. That.
Let's just say that if you miss this class, you'll go like
This is a really confusing class to miss. Uranium. Uranium to no, Evelyn. Right here. Sarah's at least facing this sort of direction when she talks to you, but you have to physically turn and miss everything I'm saying. Be a better friend. So, uranium-235. So, look over here. Inherently unstable. Uranium-235 does not want to be uranium-235. So it says, okay, cool. Alpha particle. Alpha particle shoots off into the world. And as a result, the atomic number drops 2, mass drops 4. Now that hunk slowly of uranium is slowly turning into thorium. Thorium with a mass of 231. That thorium is still inherently unstable. It's like you're in an oven where this classroom is really quite warm and you're wearing a sweatshirt, and underneath the sweatshirt you got another shirt, underneath that shirt you got a tank top, and you're just layered on layered on layered. Every time you take off a layer, it might not be enough. Take off the sweat, take off the winter jacket, and it's still too warm. Take off the hoodie, still too warm. Except every time you change clothes, you become a different thing. That's where the analogy breaks down. Thorium, still unstable. So thorium is going to emit a beta particle, an electron. And in the process, it's going to become PA is protactinum. And then protactinum, still unstable. Protactinum is going to release an alpha particle now, become actinum. Actinum, still unstable. It undergoes releases a beta particle, becomes thorium again. But thorium with a different mass. Here the mass is 231. Here the mass is 227. So it's undergone alpha and beta decay. Helium and hydrogen just spontaneously springing into existence and shooting off these things. Yeah, I know, it's weird. Thorium is going to become radon and release an alpha particle. I took a picture of the rest of the chain. So after radon, I ran out of space. After radon, it's going to become francium. After francium, it becomes astatine. After astatine, it becomes polonium. After polonium, it becomes thallium, and then thallium finally turns into lead with a mass of 207. And finally, at that stage, the lead says, I'm good. We're done. I am content to remain lead with a mass of 207. What I could do is I could say, here's uranium, I could tell you, uranium-235 undergoes alpha, then beta, then alpha, then beta. Actually, I'll read it to you. I'll tell you exactly what it does. It goes alpha, then beta, then alpha, then beta, then alpha, then alpha, then beta, then alpha, then alpha, then beta. I should be able to tell you that. Here's uranium-235. You're going to do alpha 1, 2, 3, 4, 5, 6 times, and you're going to do beta 1, 2, 3, 4 times. What do you end? I can give you that because you just do this 6 times, and you do this 4 times. After you've changed these two numbers, 235, U, and 92. If it undergoes 6 alphas and 4 betas, that means every alpha is a 4 and a 2. So you're going to lose 24 on the 24 on the mass, and you're going to lose 12 on the atomic number, but you're going to gain 4 on the atomic number. So you should end up with, I mean, getting miscounted. You should end up with lead with a mass of 207. You could do that after just having looked at alpha and beta. It would be kind of a ridiculous question to be asked, but you could do it. Here is the last form of radiation that we're going to look at. It's called gamma decay. Gamma decay is the easiest of the 3. Definitely the most dangerous, but the easiest of the 3 to do mathematically. After alpha or beta, a nucleus is often left in an excited state which is still unstable. To become stable, the nucleus releases a high-energy photon called a gamma ray. That gamma ray has no charge. That gamma ray has no mass. It just carries away some of the extra energy. It's like at the end of the day, you get home, and your science teacher gave you 90 questions of practice, and your math teacher gave you 90 questions of practice, and your social teacher wants 3 paragraphs, and your English teacher wants this, and somehow you're taking P on top of that too, and so you have to go work out a bunch, and at the end of the day, you're just like, I have so much to do! And you just let it go, and now you're just still you, but you're relaxed. And that outburst that I just gave is just like the gamma radiation, just leaving. All that extra energy's gone. And now you get to sit in your chair with your lemonade. My daughter calls it her relaxing chair. You sit in your relaxing chair and you have your lemonade. And you just are. You're still you, Evelyn. You don't turn into Malik. You're still you, but the energy has decreased. No, that had nothing to do with it. No, don't abuse the analogies. You in a beta decay, you turn into Malik. Now you get to stay you this time. You're just a lower energy version of you. You're a relaxed version. You're not so stressed and high strung. I don't know. I'm just saying if you were. When you undergo gamma, you're not anymore. So this one's easy. The only difference here is the high energy versions of these things, they are designated high energy with the presence of the asterisks here. Gamma has no mass. Gamma has no, what's what I'm looking for? Has no mass, has no atomic number, so nothing else changes. It just stays 24 and 12, or 58 and 26. Just the asterisk is gone. The high energy piece is gone. And so at the end of the day, you can just sit and be. And gamma is mathematically easy. Practically speaking, gamma is the one form of radioactive decay you desperately want to avoid. Why? Let me draw you an example. Okay, so we have a rock. Here's a hunk of rock. I don't know what it is, but Evelyn found it hiking. Evelyn doesn't realize that this thing's radioactive. Not only is it radioactive, it's emitting all 3 forms of radiation. Boom, there's one. Boom, there's another. And boom, here's the last one. On this hike that Evelyn is on, for some reason she has her backpack and a notebook, because maybe she's a sketcher. And on her little adventure, she slides the rock into her backpack, and the rock ends up between the notebook and her. The notebook is between the rock and her. What the notebook's going to do is the notebook is going to protect her from the alpha decay. Because alpha particles, those helium nuclei, are blocked by paper. A single piece of paper is enough to block alpha decay. One of these. You put one of these between you and the rock, you wrap the rock in paper, all of a sudden the alpha decay, they're going to be fine. But you've still got the beta and the gamma to worry about. Here is the beta decay. Evelyn, if you want to be sure that the rock you pick up on your next hike isn't going to mess you up with beta decay, you need to wrap it in something else. You can take a sheet of aluminum foil. Aluminum foil is enough to block beta decay. The electrons that are coming off that radioactive material are able to be blocked with just a sheet of aluminum. Brooke, does she know you're drawing on her? Okay, stop, because I'm giving notes. Unfortunately, Evelyn is almost certainly not going to be able to protect herself from the gamma because oh, that's not gamma, that's alpha. Here's gamma. Gamma is that symbol. Because gamma requires a block of lead. If she was somehow carrying a lead box with her and put it inside the lead box, lead is the vest they put on you at the dentist office when you're getting X-rays, it's a lead vest to protect you from those X-rays. Because X-rays, if you just take the X-rays and increase their energy a little bit, the X-rays will turn into gamma rays. It's the same particle. A photon is a photon is a photon. Just the more energy you give it, the more dangerous it becomes to you. Like visible photons, visible light, bounces off your skin, bounces off your clothes. That's how we see you. X-rays go through the skin, bounce off your bones. That's how we take an X-ray. Gamma rays will just punch right through you. But it's the same particle. It's just a high energy photon. They'll just sizzle their way right through your body. So much so that if the wrong object emitted enough gamma rays, it would wipe out all life on our planet. There are stars that can do this. So, here's what I want you to do. Your homework. You got 5 minutes in class and however much time tonight, because your jerk science teacher added stress to your life. This and the next page. What's going on here? Come on. You silly system. What is going on? My computer screen went blank. Okay, that's your homework. On your market set giver, it's looking at alpha, beta, and gamma decay. Tomorrow I will show you how we use these to create energy. You don't have a ton of time, but the bell seems to be back on schedule, so you should have about 5 minutes. Use this time to start. On your market set, go. Hello. There will be a recording. I will post them today before I leave.
Was there one for Friday?
There was, but I forgot to post that one. I will post that one today as well.
Thank you.
I need to figure out why this thing is no longer projecting. Did I turn it off? Oh, stuff is still on. Gamma is like a falling fish. It's like alpha, but falling. What is going on here? Oh, did this thing burn out? That would be awful if it did. Okay, what's going on here?